So hidden Markov model can also be treated as a generative model. If we have a hidden Markov model, HMM, we have all its components. We have Q, we have sigma, we have emission probabilities, transition probabilities. We can generate sequences from this while looking into those transition and emission probabilities. So let's recapitulate what components it has. So we have a sequence of symbols X, so that can be X1 through N at any particular level. We can have, for example, if we have 10 nucleotide sequence, so those nucleotides they will be coming from those alphabets which has the size of 4, A, T or G or C, and within that sequence Xi can be anything. So I can be 1, so that is the position number 1 where we can observe first symbol. So all these symbols, when they put together in a sequence, we represent it as X. Same way we have a sequence of states. So if we observe X1, maybe X1 is A, whether it's coming from coding regions, so that is one state, or it's coming from non-coding region, that is another state. So every position is actually coupled by some underlying states. So let's take this example one more time. So we have sequence that is X over here. These are the sequences coming from throws of coins. We see tails and heads. A sequence coming from both events. When we observe those sequences, there are some states which are coupled with that, which are hidden actually. So pi is actually path or the sequence of states. And there are also those probabilities within that. So probability of finding tail while it's a fair coin is half, and so on. So these are the probabilities which are associated with these events. So given an HMM, we can generate a sequence as we can start at state pi 1 according to a probability A naught into pi 1. So actually A naught is starting or 0 or null state. So actually what we are saying over here is this is the start probability or probability of starting in pi 1. While in pi 1 we can emit the first letter of that sequence X1 according to this probability. We call it as emission probability. So that is emission probability at pi 1 of X1. We can go to state pi 2 according to the probability which is called as transition probability, pi 1 to pi 2. So how the states are changed from, for example, a loaded to fair, or we can have coding to non-coding regions. So that is the transition probability of moving from one to another state. We continue emitting till we see the last symbol xn. We can look into it in this diagram also. So we are right now at 0. We are starting here. These are our states 1 through k, and what we are observing, what we are generating over here is the sequence of symbols. So what we observe is actually those symbols, but they are coming through different states. So we move, or we can start from 0, or we can begin with state 2 with a probability of A not 2. From this first state we can change the state and we can move up into this state 1. So there is a transition probability that applies, that at you have pi 1 at position number 1, you have one state, and now you are moving into another state, so is your transition probability apply. Same way you can continue. How do we get those symbols? So within each state we have the emission probabilities, so that will lead us what sequence of symbols we can generate from this. So we get a sequence of symbols. Now we are interested in what is the likelihood of that symbol. So we get our hidden Markov models, we got our states, we got our probabilities, transition and emission. How likely our sequence is generated from that model? So that thing is called as likelihood of the sequence. We have symbols, sequence of symbols X, we have sequence of states, and the likelihood of the sequence is given by P of X and pi, which is actually the joint probability, presence of both of them together. So in the probability equation we have both of them. Here we have the probability x1 through xn, and that is coupled by the path or sequence of state pi 1 through pi n. We can put the Markov chain property here in this equation. So probability of xn, the last one, while in pi n state, is, and then it's multiplied by the previous probability of the previous symbol. So here we have pi n, and while we move from pi n minus 1 to this state path. Same way we continue till we reach this first location. So we can simplify this equation where we can have all those state transition probabilities and all those emission probabilities. So that is what we can call it as, we have now all possibilities put together. So we can write it like this, and in this way we can come up with some parameters. So there are different parameters in this whole scenario. For example, moving from or starting in a fair state is our first parameter, and same way starting in a loaded state, another parameter, up till we can look into emitting a symbol 6 from a loaded die. So total we are having 18 parameters like this. So this theta represents actually those parameters. What is the likelihood of these parameters? We can count in x and pi the number of times each parameter occurs, and that will give us the likelihood estimates. So for example, we have some parameter which may be parameter 1 up till 18. So any of them we can calculate its occurrences in x. So that is given by these equations. So HMMs are generative models. So we can generate sequence of symbols while using these HMMs while exhibiting these sequence of states.